Hi, students. Today we're going to cover Chapter 9 in Zumdahl. The sections we're going to cover are 9.1, which is going to be an introduction and information contained in chemical reactions, chemical equations. Section 2, it's going to be using a chemical equation in order to understand the mole-to-mole relationships and extract information. Section 9.3 will introduce the concept of converting between masses and moles in order to use chemical equations. Section 9.4 is going to be introducing limiting reactants. This is a very common problem in dealing with chemical quantities. And finally, we'll talk in section 9.5 about percent yields and how we can use those in chemical quantities. So let's talk about, let's begin by talking about the information that we have in a chemical equation. So I want to emphasize the word equation in a chemical equation. So when we have a balanced chemical equation, this tells us a lot of things. It gives us a number of conversion factors on each side of the chemical equation that we can work with. So it gives us a number of number relationships. So here's an example. We have ethanol, C2H5OH. Let's leave the states off for now. 3O2 goes to 2 CO2 plus 3H2O. Okay. We should always make sure that the equation is balanced. And one thing I should say is that if you see a chemical equation in a problem and there are coefficients in front of the species in the chemical equation, you can safely assume that it's balanced. We're never going to ask you, or we're never going to give you a chemical equation with fake numbers there just to throw you off, right? The more common situation is that you get a chemical equation without any coefficients, and then you should check to make sure that it's actually coefficients of 1 everywhere. Most of the time, though, at this stage, it'll be obvious. The problem will say, A, balance the chemical equation. B, figure out some chemical quantities. Okay, so this equation is balanced. It turns out to be balanced. You can check that if you want to. But what this equation gives us is a number of relationships. And what we want to do is we want to see that the yields arrow is in a way mathematically equivalent to an equal sign. So this gives us a number of relationships. 1 mole of C2H5OH equals or yields 2 moles of CO2. It could be 1 molecule of C2H5OH equals 3 molecules of H2O. So we should realize that this gives us any number relationship that we desire to use, but usually we're going to use moles. Right, moles is just the default amount that we're going to use for a number relationship. Now, this can also give us relationships on the same side, right? So we want to realize that these are a series of equal signs between any pairs of things. right? So in other words, I could say that 1 mole of ethanol, C2H5OH, equals 3 moles of O2. In other words, 1 mole of ethanol requires 3 moles of O2 to fully react, right? So this is usually the way we use it in a pairwise, but we also want to realize we could continue this and equals 2 moles CO2, 3 moles of H2O, and so on, right? So in other words, it continues and yields these things. Now, one of the ways that we're going to use this over and over is to create a conversion factor or a ratio. So in this first case, what we could say is we could say 1 mole C2H5OH over 2 moles of CO2, or 2 moles of CO2 to 1 mole C2H5OH. I gave myself a little bit more room down here. But let's come all the way down here and see this relationship, right? We could say that 1 mole C2H5OH to 3 moles of O2 might be a factor that we want to introduce, or we could say 2 moles of CO2 for every 3 moles of O2, and so on. So we can get a number of pairwise relationships from our chemical equation, and we can insert these in our calculations wherever we would like to do that. All right, so let's look at this concept check. Right, here we have an unbalanced equation, right? So let's go ahead and balance that. C2, whoops, Cu2S plus Cu2O gives us Cu plus SO2. I'm going to leave the states off for a little bit more space. I hope you can see that we're going to balance the copper last, right? So let's focus on the other things here, because we can see that we need 2 oxygens on the right and only 1 occurs on the left in this Cu2O. So let's make that a 2, right? And if you look at this carefully, you can see that we can now easily balance this by simply adding a 6 to this, right? Because we have 2 coppers, 2 times 2 is 4, right? And that's balanced, right? So here's our balanced equation: 1 to 2 to 6 to 1. Now remember, very often in the quizzes we're going to be asking you, one of the ways that we can check to see if you've balanced the equation properly is to either tell us the coefficients or the sum of the coefficients. So this is something you might want to set aside or be able to identify quickly. After balancing the reaction, determine how many dozen copper atoms could be produced from a dozen molecules. Well, dozen is a number amount. Single molecules or gross or whatever. So if we choose to do this reaction in terms of dozens, we could do that. The relationships that we have here, 1 to 2 to 6 to 1, is a number relationship, and that works for dozens too. So if we have a dozen molecules of sulfide and 2 dozen oxide of copper 1. Now you can see that that's the right ratio, right? This says 1 dozen here, 2 dozen here. How many dozen copper atoms could we get? Now we can see that our numbers come down. So we're going to get 6 dozen copper atoms, right? This could be, this is just the way the problem chooses to express this, okay? Now, how would we set that up typically in a dimensional analysis? Let's do that for the next part. How many moles of copper could be produced from 1 mole of the sulfide and 2 moles of the oxide? Well, it so happens that the ratio 1 to 2 is the balanced ratio. So we could pick any of these, right? So let's pick 1 mole C2S, right? We're going to use one of our ratios here, and the ratio is going to be the relationship between 6 moles of copper, 1 mole of C2S. I get that from the balanced chemical equation. So I'm going to put 6 moles of copper here, 1 mole of Cu2S here. Now, one thing you'll notice that I have a habit of doing is I box the stoichiometric. This is called the stoichiometry ratio. So just kind of, that's a habit I've developed over the years. When I was a student, I started doing this, and I box it because that kind of picks out in my calculation the stoichiometric ratio. This is always very important. I'll talk about this a little bit more in a few minutes. So the answer is 6 moles of copper. Of course, all the numbers do not change, the ratios do not change. The only thing that's really changed is how we've expressed that number amount. So the answer is 6 dozen and 6 moles, right? So we can visualize this, of course, using molecules too. So if we have 2H2O, gives us 2H2 plus O2, right? We can visualize this as the molecules, and any set of numbers that matches the ratio works. So over here we have 2 molecules, right? This will probably represent, this probably will represent the moles of water, right? So each molecule to our mind would probably represent a mole of water. But the 2 to 2 to 1 equals a 4 to 4 to 2 ratio, right? So as long as we have this ratio that matches, we could use that to represent the same thing. All right. So this mole ratio is very important. A minute ago, I called this the stoichiometric ratio. And it shows that we've pulled this ratio directly from the chemical equation, and that relates different species in our chemical equation to each other, right? We can pick any 2 species in our chemical or balanced chemical equation that we choose, right? So here's another example. Sodium silicon hexafluoride plus sodium metal gives us silicon plus sodium fluoride. And this equation here, we see we have some numbers here, so we can assume this is balanced, right? How many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with excess sodium silicon hexafluoride? Okay. Well, we should always think about what we want. We want moles sodium fluoride. So this is going to be the way we want the answer. And we're going to start with 3.50 moles of sodium, right? So let's set up our dimensional analysis like this. Now, what I'm going to do is I'm going to write the equation in up here. Again, I'm going to leave off the states. That's not really a good practice, but if I can do that here, it really helps me because I suffer a little bit from a lack of space on this, right? All right, so if we want sodium fluoride and we're starting with sodium, so the ratio we're going to want to deal with here is 4 moles of Na for every 6 moles of NaF. Okay, so let me put that in. I'm going to put the 4 moles of Na on the bottom. I've talked about this before. Usually want to make sure I'm canceling the things I want to cancel. So I put in the thing I want to cancel on the bottom first. And on top, I'm going to have 6 moles of sodium fluoride. And I'm going to box this. That's my stoichiometry. So what I end up doing math-wise is 3.5 times 6 divided by 4, right? And I end up with 5.25 moles of sodium fluoride, okay? Now, there's another reason that I put boxes around this, at least when I'm presenting it to a class, is because many times when things get complicated, to save time or just because you're lazy or whatever, right? You can leave out the moles. So another reason that I box this is that tells me it's a number relationship that I've gotten from the stoichiometry. So if you think about it, it doesn't matter if I have 6 moles of sodium fluoride to 4 moles of sodium, 6 atoms of sodium fluoride to 6 atoms of sodium. I should have said molecules, right? 6 molecules of sodium fluoride or formula units to 4 molecules of sodium, or 6 dozen to 4 dozen. It's a number ratio. So many times you might want to represent that as some other number ratio, but I always box it so you can tell at a glance that it comes from the balanced chemical equation. Okay, so let me talk about this a little bit more. When we type this in, as I said, I box it. Let's say we're going to do this for clarity or to explain what we're doing. The other thing is we always want to put in the exact numbers from the chemical equation, right? There should be a correspondence from your chemical equation and this boxed factor. Now, let's look at this 6 to 4 factor we have, right? 6 moles of NaF over 4 moles of Na. Well, this does equal 3 to 2. Oops. It is true that reduces to 3 to 2. But you don't want to do that reduction when you're writing it down. The reason is because you want to always be able to go back to your work or your lab notebook or wherever you're doing your work and go to see that chemical equation, see where you got it from. Those 6 to 4 numbers, right? Again, they come directly from the chemical equation. And if you put 3 to 2, you go back to your chemical equation, and it means that you have to search for what that means. So it's not a good idea to do that. You should always leave that ratio, right? Again, I'll put it in a box. You should always leave that ratio the way it was in the chemical equation. All right, so let's look at another very common type of reaction. We have these combustions, right? We learned how to balance these combustions generically. And propane, C3H8, is a very common combustion reactant. If you grill outside, maybe you know about this reaction. All right, there's the chemical equation. Predict how many moles of CO2 are formed when 3.74, I'm going to write this down, 3.74 moles of propane, C3H8, are burned in excess oxygen. Well, let me say 2 things here. Whoops. When I write in my notes excess, I usually just use the letters X and S, and I don't want anybody to be confused about where that comes from. And we're often going to assume that one of our reactants is in excess. What that means is it's not going to run out, and our reaction only depends upon the other one. This will become a little bit more clear when we talk about limiting reactants. But you'll notice in these problems that we're doing early that they very carefully state that one of the species is in excess, right? And that means we just focus on the reactant that we're concerned about, in this case, propane. All right, so again, what we do is we set up our dimensional analysis. We're going to have stoichiometry here. We want to know how many moles of CO2. We look at our chemical equation, balanced chemical equation, 3 moles CO2 for every 1 mole of propane, C3H8. So we end up multiplying 3.74 by 3. The answer is going to be a little bit more than 10, right? Now, again, if you have a multiple choice answer or test or poll everywhere question or whatever it is, maybe if you just set this up even in your head, you can get a pretty good ballpark answer, right? This goes along with my beating the drum that you should know what your answer is before you do the math. So here, I know my answer is going to be a little bit more than 10, right? The only answer here on my multiple choice that's more than 10 is A, and so that's going to turn out to be our answer, 11.2 moles CO2, and this has the proper number of sig figs 3. Okay. So understanding these mole-to-mole relationships and how they fundamentally are in every chemical equation that we end up using is very important. But, however, right, we need to realize is that we use mass of our stuff every day in the lab. So let's say in practice, right? This is how we weigh, this is how we count things. We count by weighing. That's the whole thing we talked about in chapter 8. So what we need to do is we need to introduce this concept of counting by weighing into our chemical equation, right? So let's take our C3H8 example. Let me just write this down so I can use it as an example. Now, what I like to think about is the chemical equation is sitting up here, right? The chemical equation is what we're governed by, and it is the truth. It's what controls our whole process, right? But this is up here, this is a mole to mole, or any number, but typically we use moles, right? It's a mole to mole relationship. Now, very often what we're given down here in the lab, we're given grams. But we want to realize that we can't go directly from grams to grams because that's not a number relationship, right? How do we convert between these? We can only go back and forth in our chemical equation, right, at the mole to mole relationship. So that kind of puts a barrier here that until we get up here on the mole relationship, we cannot convert directly between grams to grams. Really what we have to do, right, is we have to convert grams to moles. How do we do that? We do that with molar mass. So we take our mass of stuff that we start with, we're gonna use the molar mass to convert that to moles. We're going to use stoichiometry to go back and forth at this higher level. And then when we're finished, we're going to use a molar mass to get back to the grams that we want, right? Here's our answer. This is kind of typically how we do the math in chemical equations and chemical quantities, right? We have to convert from grams to a mole level and then back to grams. So this is kind of our reoccurring problem. Here are the steps. Balance the equation, of course. Convert the masses of reactants or products to moles. Use stoichiometry to convert between mole ratios. Use the mole ratios to calculate the other thing that we want. And finally, convert from moles back to masses. Each of these little arrows I drew in here is going to be another calculation. Right? So the slides or the book presents this a little bit differently. They would do grams up here and they think about moles down here, but it's kind of the same thing. It's just two different levels, grams, moles. So we take the mass of our reactant, right? We're going to calculate moles of reactant. We're going to use the stoichiometry of the chemical equation to convert to moles of our product, right? And then we're going to use another molar mass calculation to get the mass of the product. All right. So let's do this in a simple example. Okay. Here we have a pretty simple chemical equation, right? But this is unbalanced. Cr plus O2 goes to Cr2O3. There's our balanced chemical equation, right? I did that very quickly, but if you need to take a second to figure out how that's balanced, go ahead and do it now. That's fine, right? And the question is, how many grams of chromium-3 oxide can be produced from 15 grams of solid chromium and excess oxygen? So let me write that down. Here's the way I'm going to think about this. 15 grams of solid chromium, and again, we have excess oxygen. This is just like burning chromium in air, right? We're not going to run out of oxygen in the air. It's everywhere. So we want to figure out the mass of CrO2 produced by Cr with excess O2. So here's what we're going to do. We're going to convert to moles of chromium using the molar mass. We're going to use a stoichiometric relationship between chromium and chromium-3 oxide, right? That's going to be my box. And then we're going to come back down and use another molar mass to get grams of Cr2O3, because remember, we can't go directly this way, right? That path is barred to us. So we're going to take an indirect path to get there. So let's see how we write this out. 15.0 grams chromium. Now, the first thing we need to know is the molar mass of chromium, right? The molar mass of chromium happens to be 52 grams per mole. So I put 1 mole chromium, 52 grams of chromium, right? And chromium-2 oxide, usually I have to say that when we do a problem like this, the first thing you're going to want to do is write down the molar masses of each of the species. It turns out the molar mass of Cr2O3 is 152 grams per mole, right? So we'll need that. All right. So if on our calculation I have written down here, if we stopped right now, what we would have is moles of chromium. We want to now do this second part. 1, 2, 3. We want to do the second part now. Use the stoichiometry. From the balanced chemical equation, we can see there's 2 moles Cr2O3 for every 4 moles of Cr. And again, I'm leaving that ratio as 2 to 4, not 1 to 2, which is equivalent mathematically, but if you wrote it that way, you would lose information. All right. The last step now is to convert to grams of chromium 3 oxide. Right. And so there's our steps. And what we should notice with good dimensional analysis is the grams of chromium is going to cancel, the moles of chromium is going to cancel, the moles of chromium 3 oxide is going to cancel, and we're going to be left with grams of chromium 3 oxide. Right? Here's the calculation laid out, and it turns out that the mole ratio is 0.144, right? But the solution here in the slides is going to be a little bit more step by step so you can see each step. I laid it all out in a longer calculation. Now, at this point, some of you are probably pretty good at dimensional analysis and you can lay this all out in one step, right? That's okay. But for some others of you, you're going to want to do this step by step, right? So if you want to do it that way, that's fine. Let me move that guy up there. So let's see what these in-between steps are going to be, right? If we stopped right here, right, we would get 0.288 moles of Cr, right? And if we stopped right here after the stoichiometric conversion, we would have 0.144 moles of Cr2O3. So those are kind of like the intermediate steps that are hidden if we just blast through all the math in one step. If we do go through this all in one step, the answer we get is 21.9 grams of Cr2O3. So that's our answer when it's all said and done. If you have to do it step by step, that's fine. Doesn't matter as long as you are able to understand the problem. And as you get more experience with this, you'll be able to build it all up and trust yourself to do it all in one step. Okay, here's another example. You should be able to get this answer from the example. I'm not going to do this example. I'm going to let you do this one on your own. Okay. And here's another one that you can test. Why don't we go ahead and do this one? PCl3 plus 3H2O goes to H3PO4 plus 3HCl, right? You can see that if we start with 20 grams of PCl3, here we put that here, right? We need the molar mass of PCl3, which happens to be 137.32, right? Our stoichiometric ratio is 3 to 1, so we get this. Notice that I boxed these on the slides too, so you can see immediately where those stoichiometric factors are. And finally, we need to multiply by the molar mass of water, which is about 18. So if we do this, we happen to get 7.87, almost 8 grams. Now let's look at a little bit different problem. We can also use chemical quantities to give us some information we may not know. Let's look at this reaction. Here we have an unknown species X. 6X reacts with B2O3 to give B4X3 plus XO2. This looks pretty complicated, right? But what we want to realize is the balanced chemical equation gives us a mole to mole relationship, and that can help us figure out the moles part of molar mass. Let's see how this works. We have 175 grams of X, and this reacts with diboron trioxide. So again, it's implied here, but we actually are going to have enough of that to react in excess, and we get 2.43 moles of the B4X3 product. What's the identity of the product? Well, let's think about this. Remember, we have the ability to use any two species in our chemical equation, equate them to each other to use as a stoichiometric factor. So here's the way we're going to do this, right? Here's the way we're going to do this. We have the moles of B4X3, and we have the balanced chemical equation. We're going to use stoichiometry to go back and find the number of moles of our X, right? And then if we put the grams that we start with over the number of moles that we used, that's molar mass. And we can use the molar mass and look it up on the periodic table to identify the substance, okay? So let's write this out in detail now. We start with the 2.43 moles of B4X3, right? Oops, we're gonna multiply this by the stoichiometry now. We're starting with moles of stuff. Now, the problem would be a little different if we started with grams of this B4X3, right? Because then we wouldn't be able to convert to moles directly. Okay, so we have 6 moles of X for every 1 mole of B4X3, right? So that's that first step is there. Then the second step is going to be figuring out this number of moles. When you do the math, it happens to be 14.6 moles of X. 14.6 moles of X is the same as the 175 grams of X. In other words, 14.6 moles of X equals 175 grams of X. So we can divide one by the other. The molar mass is going to be 175 grams of X over 14.6 moles, right? And this turns out to be 12.0 grams per mole. Maybe you know this as our friend carbon, right? Carbon's molar mass is 12, so there's our answer, right? You may have to look at this a couple times to see how this works, but again, it's because we knew the moles of product at the end. You might wonder, how could we do a chemical reaction and know the number of moles just independently? Well, it turns out one of the main ways that we do this is by using the gas laws. In a couple chapters, when we talk about the gas laws, this may make a little bit more sense to you how we could actually do this experimentally. All right, next topic we have to talk about is the concept of limiting reactants. Usually, we do not mix our species in our chemical reactions in exact or stoichiometric proportions, right? This is very difficult to do. Just think if every time you did a chemical reaction, you had to do a calculation to begin with, calculate exactly how much of each reactant you needed to react exactly with each other in exactly the right proportion. This would be hard. Usually, we do something like burn propane in air. And of course, air is an infinite amount of oxygen. There's an infinite amount of oxygen available in air, even in a room, right? We're not going to close up, we're not going to run out of air. we don't have to worry that just because we're burning a little bit of propane in one corner of the lab, that it's going to asphyxiate everybody in the entire lab. There's clearly enough oxygen to take care of this reaction. So that's what we've been talking about so far, where one species is in excess. But it's usual for one species to limit our reaction. Many times this is because it's a valuable or expensive reactant, right? And we don't want to just willy-nilly use a bunch of this reactant and waste our money, right? So we would very carefully use the amount of reactant we wanted to get the product we want, but then we introduce a lot of the other reactants to make sure this will be used up. We do this concept all the time in life, but we don't think about it in terms of chemical equations, right? If you're, let's say that you wanted to make cookies or cupcakes or something, and maybe the first thing you do is look in the refrigerator and see how many eggs you have, right? Because if you don't have enough eggs, you clearly have to go to the store. But maybe you have cake mix, or if you're the kind of person that likes to make things from scratch, you might have a lot of flour and cocoa powder and so on. And these things we usually buy in bulk. So it's usually things like eggs and maybe milk that we run out of first. So you might look at the recipe, right? Which in a way is a chemical equation. It lists a bunch of things that you mix together, reactants, to get a given number of cupcakes, say 12 or 24 cupcakes or 3 dozen cookies. And you would do a calculation in your head to see if you had enough eggs to make at least a batch of cookies or cupcakes, right? This is limiting reactants. Your eggs are the limiting reactant and everything else is in excess, right? So let's use some cartoon pictures to visualize this. Here we have this reaction. This is a very famous reaction that we use all the time. It's known as the Haber reaction. It's one of the reasons why human beings can produce enough food in general to feed populations around the world. It's the fixation of ammonia, making nitrogen as a fertilizer. Anyway, the cool thing about the Haber reaction is you can use this literally for every chemical concept in freshman chemistry. So we see it a lot. Nitrogen plus hydrogen gives us ammonia. Well, let's visualize a mixture of hydrogen and nitrogen. And again, we're going to use molecules maybe really to represent moles of these species, right? And we can go in here and we can start counting what we have, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what we've done is we've mixed 15 moles of hydrogen and put it in this container. And now let me look at the nitrogen. 1, 2, 3, 4, 5. 5 moles of nitrogen. Well, what's the stoichiometric ratio of nitrogen to hydrogen? It's 1 to 3. Is 5 to 15 the same as 1 to 3? Yeah, in this case it is. So this is stoichiometric. This cartoon is a stoichiometric mixture, right? So let me write this down over here. If we have nitrogen plus 3 hydrogen gives us 2 NH3, all in the gas state, then 5 moles to 15 moles, this ratio is the same as 1 to 3. So we call this stoichiometric. Stoichiometric is the exact ratio that the balanced chemical equation indicates, right? Now, if this reaction occurs, 5 moles of nitrogen and 15 moles of hydrogen, they're going to react completely, and there's going to be 0 of each will be left after a full reaction. And when I mean a full reaction, I mean it goes all the way, right, as far as it can go. Okay. Well, what if we have a different combination of things? What if we now have 1, 2, 3, 4, 5, right? What if we have 5 nitrogens and 1, 2, 3, 4, 5, 6, 7, 8, 9 H2s? Well, you might think in your head the ratio, the kind of magic or stoichiometric ratio, is 1 to 3. And if I have 5 nitrogens and 3 hydrogens, that looks pretty close to 1 to 2, right? So you may have to think about it a little bit, but at least you can see this is not stoichiometric. So when the ratio is not, let's start with something simple. When it's not stoichiometric, one species will be in excess, right? Now, from our picture here, the way we drew this, we can see that N2 is in excess, right? But if one's in excess, it means the other will be limiting. We call this the limiting reactant. Now, if we think about the amount of product we get, the amount of product we get is going to be determined by the limiting reactant, right? Because this runs out first. Okay, so what we can see here is we've produced 3 sets of product. In other words, 6 NH3 are formed, right? So what this says is that if we have 5 moles of N2 and 9 moles of H2, this gave us 6 moles of NH3. And once we know what the limiting reactant is, the limiting reactant will tell us the amount of product. In other words, I could find that amount by saying 9 moles of H2 using my stoichiometry, right? Using my balanced chemical equation, 2 moles of NH3 for every 3 moles of H2, right? And when I apply the stoichiometric factor here, 2/3, I get 6 moles of NH3, right? If I tried that with the nitrogen, right? 5 moles of nitrogen, 2 moles of NH3 for every 1 mole of nitrogen, this gives us a value of 10 moles, right? 10 moles of NH3. But we don't get this, right? Experimentally, we can see that we only got 6 NH3s, right? Right? This would only be true if the nitrogen were the limiting reactant, right? But it's not, right? So what we want to be able to do is first of all, we want to see that if we know what the limiting reactant is, the limiting reactant determines the amount of product. So if we can figure out what the limiting reactant is kind of ahead of time, it saves us some time, right? Because we only have to do this type of calculation for the limiting reactant. On the other hand, this illustrates one way we can figure out the limiting reactant is. what did we do here? We could calculate the amount of product from each reactant and then pick the smaller amount. Right? Both of these cannot be true simultaneously. Hydrogen cannot simultaneously be the limiting reactant with nitrogen if their amounts are not the same as the stoichiometric amounts. One of them will run out first. The one that runs out first will determine the amount of product. That's the smaller amount, right? If we have 10 gallons of milk and 50 pounds of flour and 1 pound of cocoa powder, but only 3 eggs, right? The 3 eggs are going to be what determines how many cookies or cupcakes we can make, right? So we're going to focus on the 3 eggs and figure out how much stuff we can make. The other stuff doesn't matter. Okay, so in this previous example, the limiting reactant is H2. Well, we also want to pay a little bit of attention about what's left over, right? Because sometimes this is important to know. It's important to be able to determine the amount of leftover product too. I'll come back to this in a little bit. Okay. All right, let's look at another example. This is going to be, this reaction is known as the water gas reaction. Maybe you can see why. CH4 plus H2O goes to 3H2 plus CO, right? So here's the reaction, and this is now the balanced chemical equation, pretty simple reaction. We can again draw cartoons to visualize what we're going to get. If we have 4 moles of CH4 and 2 moles of H2O, right? This is a case where, since the reactants combine in a 1-to-1 fashion, it's pretty easy to pick out the limiting reactant, right? We just pick out the smaller amount. So sometimes this is easy to pick out. Right? In general, it will be hard, or let's say harder, to determine the limiting reactant by inspection. In other words, just by looking at the numbers and figuring it out. If the amounts given are in grams, right? So we should have a methodology to do this, right? So let's run through the steps that would be necessary to figure out the limiting reactant if we're given masses, right? First of all, of course, we have to have a balanced chemical equation. Then again, remember, if we're gonna start with masses, we need to convert to mole amounts. This is going to be very similar to what we did before, but now the examples we're going to use, we're going to have 2 reactants, 2 gram amounts to convert to mole amounts. We have to figure out a way to use the balanced chemical equation and the mole ratios to figure out which one's the limiting reactant. Once we figure out what the limiting reactant is, we can use the limiting reactant to determine the amount of moles, and then finally the amount of grams of product. We're going to illustrate this with some simple chemical equations. Okay. So first, let's write down our balanced chemical equation. Right. We're going to have 10 grams of each of these species. We need to know the molar mass of each of these species. Right, and 25 grams per mole. So I'm going to write those on top. This is all information we're going to need to do this problem. All right, what mass of product are we going to get given 10 grams of each of these, right? there's, again, as I mentioned before, there's more than one way to do this. Let's do this kind of what I would call the brute force method. In the brute force method, this is the method I mentioned before. We're going to figure out the amount of product we would get from each reactant, assuming the other one is in excess, right? So we'll have two full calculations. And then we pick the smaller amount, right? So we have two assumptions. Only one of them can be correct. The first assumption is that B is in excess, and so the A determines the amount of product. The other assumption is that A is in excess, so B determines the amount of product, but only one of these can be true. The one that's true is the one that gives us the smaller amount of product. So we start with 10 grams of A. We do a molar mass calculation. 1 mole of A is 10 grams. That was given to us in the problem. The stoichiometry is 2 moles of C for every 1 mole of A. And finally, we multiply by the molar mass of C. 25 grams of C is 1 mole, right? 10 divided by 10 times 2. So this gives us 50 grams of C. This is only if A is the limiting reactant, right? So we can do the other calculation for B now. 10 grams of B, 1 mole of B is 20 grams per mole. The stoichiometry tells us there's 2 moles of C for every 3 moles of B. And again, we finish with this factor of 25 grams per mole of C. Here we can see we have a factor of 1/2 times 2/3, right? So I'm probably going to have to break out my calculator to do this. Okay, that turns out to give us 8.3 grams of C. And again, this is if B is the limiting reactant, right? Now remember, it can only be one or the other, right? And we're making the assumption for each reactant that the other one is in excess. The smaller amount of product is going to be the true amount of product that tells us what the limiting reactant is. In this case, the amount of the limiting reactant is going to be B, and these both can't be true, so this is the amount of product we get. Right? And here's the answer when we go through the slides. Okay. Now you have to be careful with this method. You have to be a little bit careful. I'd say the #1 mistake students make when they do this is they get to the end and they add these two numbers together, right? You can't do that. It's either or. So it's either or one of these two things, but not both. Okay. Now, the other way we can do this, solve this kind of problem, is kind of what we call a direct comparison of reactants. In this way, what we're going to do is we're going to say, well, we have this many moles of A. How many moles of B do I need to react all of the A? And then I'm going to compare that theoretical amount of B with what I actually have. Or I can start with B and look at A. So I have a choice of the way to think about this. I have this amount of A, how much B do I need? Or I have this amount of B, how much A do I need? They're actually equivalent comparisons. So the nice thing is you only have to do one of these, you do not have to do both, right? Okay, so let's kind of redo this in the other way, right? The other way is we have 10 grams of A. How many grams of B do we need to use all of the A, right? So here's how we do that. 10 grams of A, 1 mole of A is 10 grams, right? We look at our chemical equation. The ratio is 3 B's for 1 A, 3 moles of B, 1 mole of A. This is stoichiometry, so I'm going to box that. And we also need to know the molar mass of B, 20. 20 grams of B and 1 mole, right? So when you do this math, it turns out that you need 60 grams of B to use all the A available. But here's the thing, we only have 10 grams B. This means B is the limiting reactant, right? We need 60 grams of B to use all of the A, but we only have 10 grams. That 10 grams of B is going to run out more quickly than the A, and that way we can focus now on the B to determine the amount of product. Okay, so this other example goes through that in that way, and we get the same answer. Right. All right. So let's review the concept of limiting reactants, and let's step back a little bit and only consider it in a mole to mole ratio, right? Because introducing molar mass is introducing the mass of things, and having to use the molar mass makes it a little bit tougher. So as a conceptual check, let's just think about moles. So here we have a chemical equation, 2H2 plus O2 gives us 2H2O. Which with is we want the greatest amount of stuff that's still in the stoichiometric ratio. If we have 2 moles of H2 and 2 moles of O2, what's the limiting reactant? Well, for 2 moles of H2, we need 1 mole of O2, right? So 2H2 only requires 1 mole of O2. So this is going to give us 2H2O. 2 moles of H2 and 3 moles of O2, well, this is still the same H2 limiting reactant, right? We can increase the amount. If we have 2 moles of O2 and H2 is limiting, then if we increase the amount of O2, that's not really helping us. So this also gives us 2 moles of H2O. 2 moles of H2 and 1 mole of O2, this is stoichiometric, right? So we could pick either of these guys, and that would also give us 2 moles of H2O. 3 moles of H2 and 1 mole of O2. Well, now what we're doing is we're, instead of the H2 being the limiting reactant, now the O2 is the limiting reactant, right? Because 1 mole of O2 would require half as much H2 or only 1 mole of H2. So I hope you can see that this will also give us 2 moles of H2O. So in all 4 of these cases, we're going to get the same amount of product, 2 moles. Okay, let's look at another concept check. Here we have a reaction, A plus 3B goes to 4C. This looks similar to the ABC kind of reaction we had a few minutes ago, but it's not, so we have to be careful not use the old values. What we're given here is 3 moles of A and 6 moles of B. Let's do a quick direct comparison to see how many moles of the other we need to use up all of the one, right? In other words, let's look at A first. In order to use up all the A, we start with 3 moles of A. We use stoichiometry, 3 moles of B for every 1 mole of A. This equals 9 moles of B to use all the A. Let's write that here in red, right? Okay, let's do a direct comparison the other way. Now remember I said you only have to do one of these direct comparisons, but what we want to do is we want to make sure that we get the same answer from both ways, right? In other words, I don't want you to worry that if you picked A instead of B or B instead of A, you wouldn't get the right answer. You only have to do one of these. Well, 3 moles of B. That means we need 2 moles of A to use all of the B. Let's put that in red. All right. So if we do the first comparison, we can see that we need 9 moles of B to use up all of the A. But we have 6. That should show us that B is the limiting reactant. That comparison, right? We need 9 to use up all the A, but we only have 6. So that means that the 6 moles of B, the B is the limiting reactant. Let's look at the other comparison. We need 2 moles of A to use up all of the B. We have more. We have 3 moles of A. We only need 2. So the A is the excess. That again says that the B is the limiting reactant. So no matter which way we look at the B is the limiting reactant. So let's look and see how we can apply this to find the answer. A is the leftover reactant because you only need 2 moles of A and have 3. Well, that's true, right? A is the leftover reactant because for every 1 mole of A, 4 moles of C are produced. Well, that is true. That statement pertaining to the reaction is true, but that's not why it's the limiting reactant, right? The reason why it's the limiting reactant is the comparison between A and B really has nothing to do with C. So that's not necessarily true. B is the leftover reactant because you have more moles of B than A. Well, that's not true either, right? You have to compare them according to stoichiometry to figure out which one's left over. B is the leftover reactant because 3 moles of B react with every 1 mole of A. Well, it depends on how much you have, not just the stoichiometry of the reaction. So the only true statement here is A. Okay. Well, once we introduce grams, again, as I said, this makes it a little bit more complicated. And we have to figure out a systematic way to apply this. Really, all we have to do is introduce molar masses into our equation. Okay, so if I have 3 grams of each of these, right? Let's try to do a direct comparison way of doing this to figure out how much we produce, right? So, and remember, we only have to do one direct comparison. Let's just start with the nitrogen. 3 grams of nitrogen, 1 mole of nitrogen is 28 grams. We need 3 moles of hydrogen for every 1 mole of nitrogen. And since we're given the mass of hydrogen, we need to get the mass out of this comparison. 2 grams of hydrogen for every 1 mole. right? So once we do this math, 3 divided by 28 times 3 times 2, we need 0.64 grams of hydrogen to use all the N2. We have 3 grams, which is greater than the 0.64. What this tells us is not that doesn't directly tell us that the nitrogen is the limiting reactant. It tells us the hydrogen is the excess, which is the same thing as saying the nitrogen is the limiting reactant, right? All right. This is not the answer though, right? This just tells us which of these species we can use to figure out the amount of product, right? So now we kind of have to go back. 3 grams of nitrogen, 1 mole of nitrogen is 28 grams of nitrogen. Now we have, at this point, we do things a little bit differently. 2 moles of ammonia for every 1 mole of nitrogen. And we multiply by the molar mass of ammonia, 17.0 grams, 1 mole NH3. This gives us 3.64 grams of ammonia. Now remember, because of the little bit of uncertainty we have in every calculation, if we're off in the least significant digit, we don't want to throw us, right? The answer is here, is 3.65. Okay, we should always be willing to give a little bit on that least significant figure. Now, conceptually, the direct comparison is a little bit harder for some people, right? It means only one calculation at the beginning, but you kind of have to go back a step and then figure out the amount of product you get from the limiting reactant. So it is okay to do a direct, the brute force method all the way through and pick the smaller. Each method has kind of its own complication or difficulty. All right, so that brings us to the concept of percent yields. Percent yield is a very common thing that we do in the lab, right? Because it turns out it gives us some measure of how good our experiment is, right? Anything we do on paper any calculation we do on paper regarding the amount of product we get, we should think of this as being theoretical. Chemistry is an experimental science, and we really need to do things in the lab to see what happens, right? The theoretical amount is really an upper bound to what we might see in the lab, right? And this upper bound is 100%, right? This would be the most that we could possibly get. And as you know, when we do things in real life, it's not very typical that we get the 100% amount, right? Things are going to happen to prevent us from getting the amount that we think. So the theoretical yield is what we get when we calculate on paper, even taking limiting reactants into account, right? So in other words, the theoretical yield takes limiting reactant concept into account, but it's just the paper amount. In the lab, we obtain an actual yield, which is going to be no more than the theoretical. Once in a while, we're going to get the theoretical yield, but usually we're going to get something less than this. This is just what happens in the lab, right? Well, let's define what percent yield is. Percent yield is going to be the actual, let's call this the lab amount, over the theoretical on paper times 100. This can be no more than 100%, right? If it's more than 100%, then we've done something wrong, either in calculation or in the lab. Okay, let's do an example of this using the kinds of ABC reactions we did before. Now, we determined before that 8.33 grams of C is what we should produce. We should realize that this is the theoretical yield, right? 7.23 grams of C was obtained when we did this in the lab. What's the percent yield? Well, we should give ourselves a big hint, right? The percent yield must be less than or equal to 100, right? So if we have two masses here, we should always arrange them with the smaller one on top. .23 grams, which is our lab amount, 8.33 grams, which is our paper amount, times 100, and we get 86.8%. That looks pretty good to me. Maybe it was just because when I did labs, I didn't get great yields. Everything more than 50% to me looks pretty good. All right, so let's do kind of a full-blown example that would be considered a limiting reactant plus percent yield problem. We have a reaction 2S plus 3O2 goes to 2SO2, SO3, sorry. And we're given, well, it says we obtain 1.50 grams of SO3 and we have 1 gram of oxygen and excess sulfur. So the focus on this problem is going to be percent yield, not really a limiting reactant problem, right? Because the sulfur is in excess, then what we're going to do is we're going to compare the theoretical amount is going to come from the O2, right? All right, the theoretical yield must come from the O2 since the sulfur is in excess, right? In other words, the oxygen is the limiting reactant. So let's write out how we would calculate this. 1 gram of oxygen, 1 mole of oxygen is 32 grams of oxygen. The stoichiometry of our reaction is 2 moles SO3 for every 3 moles of O2. And then at the end, we have to multiply by the molar mass of SO3, which is 48 plus 32, which is 80 grams of SO3 for 1 mole. So this theoretical amount is 1.67 grams of SO3. Now remember, the percent yield can never be more than 100% in actuality. So we want to arrange these numbers. That's a quick and dirty way to remember how to arrange the numbers. We want to arrange the numbers so the actual 1.50 grams over the theoretical 1.67 grams is less than 1. this is 90%, right? So what we're going to do is pick the 89.8 because that seems to be the closest. Now, you need to be comfortable enough with percent yield to work back and forth, right? What if we did another reaction? But what if it was only 55% yield? What mass was obtained? If the percent yield is 55%, can we figure out the mass? From the same mass of O2 and excess sulfur, okay? Well, here's how we set it up, right? 55% equals the actual over the theoretical times 100, right? Well, we still know the theoretical yield, 1.67 grams. Let's call the actual A. So we just have to rearrange things, right? So we're going to have 55% times 1.67 grams, which is the theoretical, divided by 100 is going to be our amount. That 100 is important, right? If we leave out that 100, we're going to get kind of a nutty answer. So 55% yield corresponds to 0.92 grams of SO3. Okay, so that's it for chapter 9. The big concepts here, I should say, are being able to use mole-to-mole relationships for a chemical equation, right? The second big concept was starting with gram amounts, converting these to moles with molar mass, and then using that stoichiometry. And finally, the concept of percent yield, right? Percent yield is just a quick way to figure out the quality of your reaction or how well you did the reaction. And we use this from time to time to see if we can do a reaction better. But that turns out to be actually a pretty complicated concept. So I hope this lecture was useful to you, and I will see you next time.